So we have seen clock underscore monotonic, which is a clock which increases, which does not get affected by system time. Let's see the some other clocks which clock underscore get time provides. This all we call as POSIX clocks. So the next clock we'll be looking is clock underscore boot time. The difference between clock underscore monotonic and clock underscore boot time is clock underscore monotonic, it does not measure time spent in suspend. So if you want to measure time spent in suspend also, when your system is suspended, you can use clock underscore boot time. So this also includes the time spent by your program or the function in the suspend state. So let's see an example of this. So instead of using monotonic, we'll be using boot time. So the difference is it also includes the time spent by the application in suspend. So as we are running in VM, so it will not be much use case, but you can measure this in your native machine. So you can measure in your native machine, set your system to suspend, then bring your system back, and then check whether the elapsed time includes the suspend measure. It also includes the time the system is in suspended state. So you can try this out on a native machine. Then we have one more clock, which is clock underscore monotonic underscore raw. Though this is similar to clock underscore monotonic, but it provides access to a raw hardware based time, which is not subjected to NTP adjustment. So this means clock underscore monotonic is subjected to NTP adjustments, whereas clock underscore monotonic underscore raw, it is not subjected to NTP adjustment. So when we can use clock monotonic raw, it is useful in cases where accurate time is wanted over very short intervals. Whereas clock underscore monotonic is preferable for longer time timers, which are measured in minutes, hours, or days. So if you are measuring in minutes, hours, or days, you use clock underscore monotonic. But if you are measuring a very short intervals, you can use clock underscore monotonic underscore raw. Again, a simple program. So same program, instead of using boot time, we are using a monotonic raw clock, which is not affected by NTP adjustment. So it gives us, it takes like 5 seconds, which is what expected. We added a sleep of 5 seconds in between two clock underscore get time. Then we have one more clock. This is the real time clock underscore real time. So this gives us the real time or wall time in the system. So the same thing, which is clock underscore. So get time of day also gives us the wall time, wall clock or real clock. So same thing, clock underscore real time. So this is useful in time stamping as well as providing the actual time to the user. Important point here is it can be affected by time adjustment code, which is NTP. So clock underscore get time, it gives us the wall time. So the same thing which date gives us, it gives the same thing. So we can also have one more program which uses both. Let's use both. Say wall time 1. And then let's use time val and say wall time 2. And let's use get time of day. and pass all time to, and then print the same thing. We can both are giving the same thing. So both are giving the wall time, clock underscore get time with a clock of real time, clock underscore real time. It gives us wall time, same thing which is given by get time of day. Then we have one more clock, which is clock underscore process underscore CPU time underscore ID. This gives us per process CPU time clock. So this gives us, it measures the CPU time consumed by all the threads in the process. So it is useful for finding out whether your program is spending its total time in CPU or whether it is waiting for something else. It can be a user input. So it gives this particular clock, it will give us how much time your process is actually using the CPU. It does not calculate the time spent in waiting for user input. So amount of time, which is amount of time used by your process, which when it is actually using the CPU, you can get it by using this particular clock. So let's see this example. So the same example which we have been using from past. So here we have clock is CPU time ID. Then we have sleep of 5. And then we subtract and get. So what do you think will be the output? Will we get 5 seconds here in elapsed seconds? Or will we get some other value? What will be the elapsed seconds? If I use clock underscore monotonic, it's 5 seconds. But what will be the value when we have this clock underscore process underscore CPU time underscore ID? What do you think will have here? Will we have 5? We know that CPU, it gives us the amount of time the process uses the CPU. So let's measure it. Let's run this program. So it is running a 5-second delay. So it is 0 seconds. It only took some nanoseconds running that, but it's very 0 seconds. Because sleep is not taking the CPU. Sleep will tell the kernel to give the schedule some other process. So this is the reason it took 0 seconds. Now let's actually calculate amount of time it takes to increment a particular variable. So I have a variable I. I want to measure the amount of time that the CPU takes to increment I up to int underscore max. So I use clock get time with CPU time ID, and then I measure it and then display it. The same thing, how much time it takes to increment a variable up to u int max. So limits.h header file is needed for this, which has the hash defined for this particular thing. So let's actually run this program now. So it took 3 seconds and some nanoseconds for measuring up to int underscore max. And you can see it took 6 seconds and some nanoseconds for measuring up to u int max. So using this, you can measure how much time your actual process, how much time is taken used by the CPU. So you can keep it at the starting of your main and at the end of the main, and then you can also measure. Now here is one more question for you. So I have a variable j, which is 0, and I have a variable I, which is 10k. So I want to measure the amount of time CPU takes to divide I with 256. So I can perform this operation in two ways. One is using the division operation. The other is using it's the right shift operation. So I can use either division or I can use right shift operation, but both are performing the same operation, which is dividing I by 256. So now let's measure the amount of time here, the amount of time here. What do you think, which will be more, or both will be same? Will it take same amount of time? Will it take different amount of time? And if it takes different amount of time, which will be faster? Think for some time. So let's, by the time you think, let's run the program. So now you can measure here which is faster. Let's run it multiple times. You can see the difference here. Which is faster? The one which is using right shift is faster. The one which is using division operation is slower, because right shift it may have will have a direct assembly instruction for that, and it has support in the architecture, so it is fast. Now let's compare the both clocks, clock underscore monotonic and CPU time ID. I accept a user input using scanf. So I have a integer val. So I have a val integer variable. So I use two clocks now. I want to measure the monotonic time as well as the time spent by the CPU. So I keep it in between scanf. So I measure the start time and then I measure the end time for this particular function and I display it. So which one will be like which time will be less, when whether monotonic time will be more or whether CPU time will be more? Let's see that. So now it's waiting for a user input. Until we give a user input, this will wait. So I gave a user input, so it completed scanf. And you can see scanf, it was not actually using the CPU until there was a keyboard interrupt and then scanf became running on the CPU. So the CPU time used is 0 seconds on scanf, whereas monotonic time is a total time elapsed in between the user input and the scanf call. So you can see CPU time is only the time the clock will give you when the process is actually using the CPU, whereas a monotonic time is a time which is continuously ticking up. Then we have one more clock, which is clock underscore thread underscore CPU time underscore ID. This will give us the amount of CPU time consumed by the thread. So we have the previous one is the CPU time consumed by the process. Now, if you want to have the CPU time consumed by a particular thread, you can use clock underscore thread underscore CPU time underscore ID. So I have a thread. So now I am using real time, which is the wall clock time, whole process CPU time. This is a thread CPU time. I create a thread, and this particular thread actually increments a variable up to int max. So, and it is measuring the thread CPU time. So it is wrong here. It should be thread CPU time ID. And we are also measuring the process CPU time ID. It should be thread here. So we have main thread. We also have another thread which we create. So we are measuring both threads time as well as we are measuring the process time, and then we are printing it. So let's see the output for this. We need to compile it with LP thread. So this is a thread time which was incrementing I up to int max. The main thread was incrementing up to uint max. So the thread took 3 seconds. Main thread took 6 seconds. And the whole real time is 10 seconds. But you can CPU time is 9 seconds. So you can see 3 plus 6 is 9. You can run it one more time. So this is the thread time. It took like 3 seconds. And the main thread is 6 seconds. Real time for this is 10 seconds and 9 seconds. Then we have one more function. Till now we have retrieved the values from the clock. Then if you want to update the clock, you can have one more function which is clock underscore set time, which will set the time of a specified clock ID. So clock underscore set time, it takes two values, clock ID and the time you want to set. Till now we have been using clock get time. Now this is for setting a time. Let's see an example of this. So we are getting the real time, and then we are incrementing like seconds, like 10 into 60, it's 10 minutes. And then we are calling clock set time, and then we are calling clock get time, and then we are getting the time. Printing again using C time in a human readable format. So it needs, so the current time is 7:30. We are trying to set it to 7:40, but operation not permitted because we need sudo. As we are setting time, we need to be a sudo super user. So now we have been successful in getting the time. So you can see here, the initial time was 7:30:47. We set it to 7:40:47. And when we call clock get time, we got 7:40:47. Let's verify with date, but we have 7:31. This is because the NTP service has reset the time back to the original network time. So if you stop the NTP service, then you can see the time which is set. The time when whatever time you have set in the program will be reflected when you call date. So you can see the status whether NTC is running or not. Yes, time date control. Status will tell you whether what is the local time and what is the time zone, etc. You can see here it is active or not. System date time sync. So if I stop this service time sync, it will tell us it is not active. So needs sudo, so I can also type here sudo. Now I can say time status. It's not activate, but it's saying yes, it's active. So maybe some problem here. So now let's run our program. And now you can see date has been updated to 7:42. From 7:32, we have added 10 more minutes and it is now 7:42. So let's start our service back, and it should revert it back to 7:32. So it is what this works. Then we have clock monotonic. I get the current clock monotonic time. I update 10 minutes on this set time, and again I call clock get time with clock monotonic. Let's see what will be the output for this. So this code, it gets the current monotonic clock, it increments it by 10 minutes, again by calling clock set time, again it calls clock get time, and then it's prints the value. Let's verify whether 10 minutes have been added or not. Let's run without sudo user, says invalid argument. So clock get set time cannot be used for monotonic clock. It can only be used for real-time clock, which is the wall clock. So you cannot use clock underscore monotonic for, you cannot use clock underscore set time for clock monotonic clock. You can only use it for real-time clock. We have one more function provided by POSIX clocks, which is clock underscore getRes. So clock underscore getRes function, it finds the precision of specified clock. So whether the clock is having nanosecond precision, whether it is having microsecond precision and all, it can be find out by using clock underscore getRes. You have to specify the clock ID, and then results will be stored in time spec. So here in this program, we are trying to get the resolution of real-time clock, monotonic clock, and boot time clock, process CPU time clock, thread CPU time clock. I'm printing the resolution here. So you can see here, they are all clocks have nanosecond resolution here. All the clocks are having nanosecond resolution. Then we have one more system call, which is times. It accepts struct TMS. This particular call, it gives us both the time spent in user's process, user mode, as well as in kernel mode by the current process and its children. So if you want to find out the amount of time spent in user mode as well as in kernel mode, which is the system time, you can use times. It uses for your current process as well as for the children process. It gives us for both user and the children process. All times they are reported in clock underscore ticks. So you can see here it's clock underscore tick. So number of clock ticks per second you can obtain by using this particular function, sysconf. So time is reported in clock ticks, and how many clock ticks per second you can find out by using this particular function, sysconf. So this is useful if you want to find out user time as well as system time. So to get the clock ticks, number of clocks per second, I use this particular function. I stored it here, sysconf in this. I call a function spend time, where I actually just spend some time by opening dev view random. I read some random values. I close the dev random. So I do this for some time, and I open dev 0. I perform the same operation, and I just, so opening dev 0 means reading and all. It is happening kernel space. So it is a character driver. That particular read function of the character driver will be called here, and then I'm spending some time in user space by just incrementing a local variable. Then I'm calling times, and I'm printing the user time, system time of the current process as well as children process. So it says the number of clock ticks per second is 100, and it is now spending some time. So we don't have children, so they are zeros. User time is 656, which is actually 6 seconds. The time it's spent in kernel, it is 96 ticks, so it is 0 seconds. So it was dividing 96 by 100. We should have used float here. So we can also use time. Time also gives the same of what it is. System time and user time. So you can see here, it took like 645 ticks. and 93 ticks. So it gives the user time as 6:45. You can see here 6 seconds, 4:55, and then system time it gave us like 93 ticks, so 94. This is the real time, which is the amount of time spent by the application. Then we have one more, get R usage. So get R usage also is like times. It use different resource usages. So as we are looking to timing, one of the resource we are looking here is time, use CPU time and system CPU time. So we can get the resource usage of self or of a particular children process or some thread. And it returns a struct R usage. And you have two important fields which we are looking now: user CPU time and system CPU time. The same function, instead of using times, we are using get R usage. I'm saying give me my usage, resource usages. It gives us in seconds and microseconds. So we do not have the clock ticks here like the previous one. So it gives like 6 seconds and microseconds. It gives in time. So it is giving it in, let's see what is that it is giving. It's giving it in time val, not time spec. So it has a microsecond resolution. We can also compare this with time, the result with time. So the same thing is here, 6.650, 6 seconds, 6:49. System time is 0.948. So it is what time uses the same APIs. So this is all about the different clocks, the different timing in user space. Let's move to quiz now.